going to start us right into endocrine, and then we'll get going for a little bit, and then we'll take a break, okay? So endocrine disorders. So now we're caught up. We may not get through this whole thing. That's okay. We'll get caught up. Exocrine versus endocrine. So endocrine is referring to this system of glands that typically are going to be releasing a chemical signal. Oftentimes it's a hormone. It goes into the bloodstream and it causes a global response throughout the entire body. The system that's typically compared and contrasted to the endocrine system is the nervous system, which is where we were 2 weeks ago. So the nervous system operates very quickly, right? An action potential can be sent, you can go to a specific target organ, and you can immediately cause a change. But you could be very local about it. You could cause just a reaction in that particular space through the nervous system. The endocrine system is identified to be more slow-acting, but broad-based. So you don't release a hormone and expect it only to go to the big toe, okay? You wouldn't release a hormone and say, oh, I only want it to affect the lower half of the body. The hormone is going to be released into the system, and you're going to have entire organismal effects. So, difference between the nervous system and the endocrine system, you got local versus broadly realized. You have rapid versus maybe slow or more methodical over a period of time. Okay? So, think about puberty. Puberty, the onset of puberty comes through hormonal changes in the boy or the girl. And it doesn't happen overnight, right? I have teenagers in my house, so it'd be nice if it was overnight, but it doesn't happen overnight, okay? Happens over a period of years. And so puberty is a great example of hormonal changes that happen broad-based, and you think about all the different changes that happen in a young boy or a young girl becoming a young man or a young woman. Okay? But it's not really regulated by the nervous system per se. It's more the endocrine system. Now, the exocrine system. These are also glands, and they release a substance. It may not be a hormone, but it can be. It could be other types of chemical signals, or it could be nutritional agents like salt or potassium or fluids, secretions. And these exocrine glands, they make their products and release them via ducts onto an external surface, fleshy. So exocrine sweat glands, for example. Mammary glands, exocrine mammary glands. A lot of our exocrine function of the pancreas for digestion. The external surface is the inner lining of the intestinal system, which is technically outside of the body, right? Okay, now we've got paracrine. A lot of crins today, right? And we have autocrine. Paracrine is talking about releasing a chemical signal, and it's going to have activity on surrounding or neighboring cells. They could be adjacent, they could be a couple doors down, they could be across the street, but they're nearby. They don't necessarily need the bloodstream to transport the signal to that cell. Simple diffusion from where it was released to a cell within that diffusive distance is sufficient for paracrine. And then autocrine. Autocrine is the cell releases a signal and it binds back to the same cell and causes a response. Okay? These are all review terms, but I wanted to slowly work our way into this endocrine lecture. We have different types of hormones. We got 4 main classes. Peptides, which are proteins, or I should say, proteins are made up of peptides. That's a better way of saying it. We have steroids. Steroids are an organic compound. They usually have 4 cycloalkane rings. They're joined to each other in a loop, in a circle. And some examples of these are like estradiol and testosterone, estrogen and testosterone. An anti-inflammatory agent known as dexamethasone is also a type of steroid. Cholesterol is a type of steroid. And many of these steroids are derived from cholesterol as a base molecule. And the last monoamines. I forgot monoamines. So monoamines, these usually come from tyrosine. And monoamines examples are norepinephrine, epinephrine, dopamine, and the thyroid hormones. And then the last category, our 4th category of icosanoids. These are made from 20 carbon chain molecules that are derived from arachidonic acid. So if you remember back to our inflammatory lecture, when we talked about arachidonic acid, you guys remember that? What were the examples of products that we made from arachidonic acid? You guys remember those? Leukotrienes, thromboxanes, prostaglandins, and then one more was prostacyclines. But you did a really good job. That's exactly right. So that slide from arachidonic acid, those are all examples of icosanoids. Okay? How do they work? Well, they utilize receptors. These receptors have a very high specificity only for that molecule. And they have a saturation point, meaning that they can only bind so many of that molecule. They can be amplified, right? The signal can be increased. They can be upregulated or they can be downregulated. So you can turn that signal up or you can turn that signal down. Bless you. So there's an example here on the right side of the slide that's showing you how you can amplify or how you can upregulate and downregulate these signals. So we've got a small stimulus that triggers a hormone, and then you create through a reaction cascade a metabolic byproduct that triggers a larger effect than what you started with. And there's really kind of 2 ways that this can happen with hormone activity. So in this particular example right here on this left side, we've got these purple receptors at the cell phospholipid bilayer. We've got our hormone that can bind. Well, if you want to upregulate the signal, instead of just having, say, 3 receptors, you can upregulate it to have, say, like 10, and now you can bind more hormone to more receptors, and you increase or amplify this greater effect by upregulating the insertion of the receptor. Okay? Down here, this is cut off, but this says downregulation on the bottom black part of the screen. So likewise, you can say, well, I want to lower this response to this signal, so I'm going to decrease the number of receptors that are inserted at the cell interface. And even in the presence of the same amount of hormone, I have lower activity. Okay? Pretty straightforward. Should be very much review. I'm just trying to warm you up until we get to our clinical stuff. We got 3 main types of interactions that I want you to be familiar with, that I want you to understand well. And we're going to have examples. There's lots of white space on this slide, That should be a clue to you that I want you to write some stuff down, okay? We have synergistic activities, we have antagonistic, and we have permissive. Who can define synergistic activity for me? Or a synergistic effect?
The combination of individual effects has a greater output than their effects separately.
Okay? That's pretty good. So even if you modified that and said if you added their two effects together, that the result is greater than the sum of the addition. Okay? So for example, 1 plus 1 equals 3 would be synergistic. Okay? That's biological math. That drives the engineers incredibly bad. Okay? 1 plus 1 equals 3. So let me explain. Follicle stimulating hormone plus testosterone will lead to adequate sperm production in a male for fertility. If you have plenty of testosterone but not enough follicle stimulating hormone, sperm production levels will be too low. You need both of them together. They act synergistically, meaning the output is greater than the sum of the two parts. Okay, so 1 plus 1 equals 3. So that's a great example of synergistic effect, biologically speaking. Antagonistic effects. Anybody want to take a stab at this one? This one's pretty straightforward. Yeah. So they have competing activities, opposing actions. So insulin and glucagon are the best examples that I can think of. Insulin lowers blood glucose levels. Glucagon raises blood glucose levels. Permissive activities or permissive effects. One hormone enhances the target's response to a second hormone. Permissive. So, in the female cycle, estrogen stimulates upregulation of progesterone receptors. So, that's permissive. So it's not enough that estrogen has its own activities, it actually causes the target tissue to be more responsive to progesterone. And that's why estrogen and progesterone are so critical to the 28-day menstrual cycle. So, I really like this graph, this diagram, because it shows the complexity of the endocrine system. And I have a tremendous amount of respect for endocrinologists. When my oldest daughter was really young, we started visiting with a pediatric endocrinologist. She was, she had a disease they called short stature. When I was young, they just called me shrimp. But now they've labeled it as short stature, okay? To maybe make sure that the parents don't feel self-aware or have, have emotional problems with it. But my wife's like about 5'1", and so we don't have tall kids, right? But the pediatrician's like, oh, well, she's pretty short, she's pretty low on the growth charts. And I would look at the pediatrician and I'd say, well, my mother, her grandmother, is not even 5 foot. She's like, really? Like, yeah. Well, but let's get her tested. So we started getting her tested. And if any of you have kids, or when you have kids, getting your kids tested for different things is very stressful, okay? Because you never know what's going to come back. And especially in endocrinology. Because they started talking about, well, we're worst case scenario, we're kind of worried about a lesion. Like, a lesion where? Like, I'm looking at her, she looks fine, Well, a lesion in the brain. Oh. Okay, and this is before I was teaching this class. And so I get out my physiology textbooks and say, okay, what is she talking about? Well, she was talking about the pituitary gland. And that sits in the brain. And was worried that my daughter might have a tumor in the pituitary. And that she wasn't releasing enough hormone to have activity on her thyroid. Well, long story short, she's fine. She is short, okay? Newsflash, okay? But she's fine. She's super healthy. She actually does have low thyroid levels, so she takes a thyroid pill every morning. But she just passed her driving test this morning. Okay? Congratulations to my daughter. And so the hair's going to go more gray. But so now she's got her driver's license, and she can reach the pedals. Okay, so everything's fine. She's not so short she can't drive a regular vehicle. You know, pretty much the steering wheel's like right here. But you know, but she can drive, and she just has to manage it with a thyroid pill, a thyroxane every morning. But when we were walking through this process, I would pour over this as I was looking at, okay, so the hypothalamus is in the brain, right? Hypothalamus just below the thalamus, and it extends down to the pituitary gland. You can see there's a front portion, the anterior, and there's a back portion, the posterior. This is more neurons, and this is more endocrine. And the activity of the anterior pituitary has many different axes of activity that you explored in 202, okay? And so this would be a really healthy chapter to review in 202, the endocrine chapter, so that you can understand what we're going to talk about is when everything goes wrong. But you kind of first have to understand how it works normally before you can understand how it goes wrong. And everything in endocrinology is either it's normal or it's upregulated or downregulated. So we have hypersecretion or we have hyposecretion. Does that make sense? So if you don't know where the normal set point is, it's kind of hard to figure out what's happening in this question if I'm hypersecreting or I'm hyposecreting. Okay? So it's good to know what does it do normally. Yeah?
Like, do you want us to go back and memorize like the numbers of how everything is?
No, you don't need to memorize the numbers. No. I don't want you to go back and memorize the numbers. In fact, most of everything that you need is going to be in this lecture. But if there's stuff that you're a little bit weak on and you're curious, maybe dive into it a little bit deeper. You don't need to memorize the numbers. Okay? All right, so we're going to take a look at all these different axes, and there's a little mnemonic that's pretty good, right? There's a bunch of them out there. This one's clean. Okay? If you need one that's not this clean to remember, you know, go for it. But this one's good for public consumption in YouTube, right? Frank likes taking showers so that he appears clean, tall, handsome, and professional. And so you can see all of the different hormones and their activities. FSH, follicle stimulating hormone, luteinizing hormone, thyroid stimulating hormone, somatotropic stimulating hormone, also known as human growth hormone. And then ACTH, this is adrenocortical cortisol hormone, corticotropic hormone is what I've learned it as. And then prolactin, right? And so this is the activity of the anterior pituitary. Another picture. Again, all of this is review from 202. But I know that it's a little while ago. We've got the hypothalamus that sits up here below the thalamus, and it feeds into the anterior pituitary. And the anterior pituitary, the front portion of the pituitary gland, is the true endocrine organ. And it operates through this portal system. And this portal system allows for the transfer of venous hormones into the venous circulation. Now, if you look at the posterior aspect, this is really an extension of the brain. The posterior lobe is really axons that come down, and the posterior pituitary is really only responsible for oxytocin and antidiuretic hormone, also known as vasopressin. Okay? Oxytocin, if you guys remember, this stimulates uterine contraction as well as lactation in the female. And then vasopressin, or antidiuretic hormone, this actually causes arterial contraction and raises blood pressure. It helps to conserve water, vasopressin. Okay? The major activity of the endocrine functionality of the pituitary comes from the anterior lobe. And you can see follicle stimulating hormone, luteinizing hormone, thyroid stimulating, adrenocorticotropic, prolactin, and growth hormone. And that's this mnemonic, right? Again, growth hormone here is called somatotropic hormone, also known as growth hormone. And then ACTH, they're calling it adrenocortisol hormone. I've always learned it as adrenocorticotropic hormone, right here, okay? And then what comes from the hypothalamus? All the releasing hormones. So this axis that I'm talking about is the hormone actually signal originates in the hypothalamus. The releasing hormones are made. They have activity, that's what these TRH, these are all releasing hormones. They have activity on the anterior lobe, and then they have activity to release and go to certain target tissue. Like, so for example, thyroid releasing hormone from the hypothalamus stimulates the anterior pituitary to manufacture thyroid stimulating hormone that has activity on the thyroid to make T3 and T4. So in my daughter's example, when, and the pediatrician didn't say this in this way, but this is what I heard. I think your daughter might have a brain tumor, right? I'm like, what the, right? She didn't say it that way, but that's what I heard. She's talking about a lesion in the hypothalamus, or maybe a lesion in the anterior pituitary, or there might be something wrong with the thyroid, right? And I'm like, well, I'm going to go with option number 3. There's something wrong with the thyroid, right? Because you don't want to think that your little girl's got something wrong in the brain, and that there's a tumor up there. But that does happen, and we're going to talk about that today, okay? So you've got releasing hormones here that cause stimulating hormones here that cause activity for hormones to be released out in the periphery. Very complex system. You guys follow? Does this make sense? Do you guys remember this? Some of you might need to brush up on it. If you do, that's okay. Okay? All right, so it's important that we have that background, and I know we took a lot of time to get to that background, so let's take a break, and then we're going to start diving into the disorders. Okay? So take a 5-minute break, and we'll dive into the disorders.